Gone, the nuclear fission process. It's a whole different story. Then we have high gamma emitters, and it is very radioactive. So we'll talk about that later when we get in there. So, 241 fuel assemblies in each reactor. We're designed to run the reactor for a year and a half, 18 months, each of our 3 units. At the end of 18 months, we do shut down and we replace roughly 1/3 of the fuel assemblies that are in there. We reshuffle the rest, basically take the outside ones, bring them to the middle. It's like a big charcoal barbecue fire, okay? And then we'll take roughly 80 fresh new fuel assemblies and put those on the outside. So we do all of our fuel shuffling, if you will, in a batches of 3. So since we do it every 18 months, we get a brand new one of those. It's going to last us 3 of those 18-month periods, about 4.5 years before it comes out of the reactor for good. We'll talk about where that goes when we get inside. Our refueling periods run roughly 30 days. It is the only time that we intentionally plan to bring the reactors down. Other than that, all Palo Verde units run at full power. And as you drove in this morning, you saw the result of us running at full power if you looked out towards the west. You saw a large white cloud coming up over there in the distance, right? Everybody see that when you came in? That's not steam, it's not anything radioactive, it's water vapor coming off the top of our cooling towers. It's getting rid of the leftover heat from the process, which we'll talk about. You'd see the same thing from a coal burning plant, but there aren't any coal burning plants nearly as huge as we are here. So what you saw is warm, moist air coming up. You saw a cloud being formed. And we do the same amount in the summertime, you just don't see it because the dew point's too high. So that's why. Nothing radioactive to it, it was just warm, moist air. Okay, any questions before we start?
How much does one of those cost?
About $1 million. About $1 million on it. But we get our money's worth because we are based on what it costs us for fuel, all the other costs that are associated with running the plant, the efficiency that we get to run it, and the fact that we can run day or night at full power. Our cost of electricity is still the lowest of any power plants we've got on the system, including coal burning plants. The only exception would be any hydro plants. They can, of course, make electricity cheaper. But most of the utilities in Arizona don't have any hydro plants that are any great size. SRP does, but you got to realize each one of our Palo Verde units is producing for delivery on the grid. In other words, this is after we've tapped off everything to run the plant. We're actually putting out on the grid 1,410 megawatts of electricity. Your bill comes in kilowatt hours. So in kilowatts rather, that would be 1,400,000 kilowatts of electricity on a continuous basis. I think the biggest dam that Salt River has on the Salt River is something like maybe 2 megawatts or 2,000 kilowatts. So it's a whole scale bigger than anything that you've got on the hydro. Palo Verde's electrical output on a yearly basis is equivalent to about 7 Hoover dams. Give you an idea of what we put out. Yeah, sure.
How long does it take to shut down a reactor?
About half a second. Okay.
Because, there's been a lot of talk lately about the threat of electromagnetic pulse attack, which could shut down the entire electrical grid.
Yeah.
And if that happens for a long period, would you be able to shut these reactors off so that there'd be no...
Yeah, see, that's not the problem. Shutting down's not the problem. Keeping it cool after it's shut down is. And that doesn't have anything to do with the grid. That has to do with electrical systems we have right there at Palo Verde to provide electricity to keep pumps running to circulate water. Once we start the nuclear reaction in the fuel, we can shut down the nuclear reaction in a second. What we cannot shut down is what we call decay heat, and I'll explain exactly where that comes from. But a good analogy or a good similar comparison is if you think of an electric stovetop. Okay, I can shut the electricity off to those burners in a heartbeat, but I can't cool the burner down right away, and that's exactly what happens here.
Are your backup power supplies hardened against EMP?
They're not only hardened, they're not tied into the grid. They're direct wired. So there's not a problem that EMP is going to take care of that, yes. Now, to get an EMP pulse, big enough to do it. I don't know that much about the sources of EMP, what you can do to use it. But it would almost take a nuclear burst in the air to do that.
Well, that's what the threat is.
Yeah, well, if we've got a nuclear burst over Palo Verde, gentlemen, we got a lot more problems than just Palo Verde shutting down.
Everything we shut down.
Everybody got ahead. That's war, and that's war to the Third World War degree, if that happens. We've done everything we can to protect the plant, but in a case, Palo Verde is not resistant to an atomic bomb going off. I don't think, well, there is nothing on this planet that is. You just can't make it that good to withstand an atomic bomb. Yes?
My understanding was that the nuclear blast, which they would use to set off an electromagnetic pulse, which would take out everything that's electrical, wouldn't do any other type of destruction. All it would do is shut down everything that's dependent on digital electronics.
Yeah. Yeah, that's probably true, but if somebody has that sort of intent to do that, I don't know what would happen. Yes, it would shut down the grid, things like that. Anything that relies on electrical pulses to work would be disrupted. That's true, you're absolutely right. That's such a scenario, though, that it's almost beyond, well, we're in World War III.
Well, the researchers have said that if that would happen, and
why would they be dead from the electromagnetic? You said from the pulse they'd be dead?
no, not from the pulse, from the not having water, not having food, not having transportation, not having water pumps, gasoline pumps, nothing.
Well, I'm not an expert on electromagnetic pulses, okay? But to do that, you'd have to shut it down everywhere, which would be, I don't know, 10s, 20s, 30 nuclear bombs just over Phoenix.
What?
Where would it be?
200 miles
100 miles
wouldn't
out.
kill a single human being, but it would wipe out every computer, everything else.
200 miles up, boy, that's a lot of atmosphere it would have to go through. I'm not so sure, I don't know.
Could be done,
It's
could be
true.
done from a satellite.
That's what Iran is working on right now. They just need the rocket to get it up there.
So then we retaliate the same way, and then the whole world's back in the Stone Age.
We can't retaliate because it would shut down our GPS system. That's what all of our military is based on. They got rid of wireless antennas. They got rid of all of that stuff.
So in other words, we're just sitting ducks. We can't do anything to defend
We are.
ourselves.
Well, if there is,
I'm not sure I can believe that, gentlemen. I really can't. I think smarter minds than ours have probably looked into that
I
and said
hope
we've
so.
got a preemptive way we can get around it. I just can't believe that.
They have the ability to harden the grid against such an attack.
And how do we do that?
But the politicians aren't doing it. All the transformers, all the 2,000 high voltage transformers all around the country need to be hardened against that EMP attack.
I don't know. But then you've got the local lines. They're going to be susceptible to it too. It's not just transformers. You're going to have everything. I don't know. That's a scenario. What if the sun has a solar storm and it could do the same thing? Yeah.
So, as a slightly different question, but along the similar topic, can you talk about why a common nuclear plant can't actually explode like a bomb?
There's two reasons. Number one, we don't have the right enrichment of uranium to do that. We can talk about that in a bit when I get into the physics part of the plant. It's not the right enrichment to cause it to go off, and the nuclear fuel is not, believe it or not, in the right shape to cause a self-sustaining chain reaction to go to such a magnitude as to cause an explosion. Because we have the fuel spread out like that, there's a term for it, it's called buckling. And buckling is a factor that you have to use to calculate how much uranium you need to cause a uncontrolled chain reaction. The ideal shape for a nuclear bomb is a sphere, because that way you would have the greatest volume to the smallest surface area. And to get in technical, it has to do with the neutrons needed to cause this chain reaction will leak out prior to being available to cause fission of the next generation. The first bomb we dropped on Hiroshima was a uranium bomb, and it was a gun-type bomb. Basically, they had a sphere of enriched uranium with a core taken out of it, like plugging an apple. And that core was at the other end of a tube with explosives behind it. By itself, that core, that sphere with the core removed, was not in the right geometric shape to cause an uncontrolled prompt chain reaction. When they slammed that plug into it, it then became so. But as soon as that infinitesimally quick chain reaction starts, it begins blowing the uranium apart, okay? Because you want everything to split, every atom in your mass to split at the same time. Well, they don't when you have a shape like that, and I think they calculated that a bomb at Hiroshima maybe used 24% of the uranium actually split. Pretty good explosion, but it's just the way the shape is. That's called buckling factor, and it has to do with the shape of it. We don't have anywhere near that. But the biggest thing is we don't have the right kind of uranium. It's the wrong enrichment of the isotope you need. And I can talk about that later. So.
And what about why we can't have a Fukushima-style accident here?
Well, number one, we're not very close to any tsunamis. Okay. So that's the main reason. We don't have our electrical system susceptible to a tidal wave, and that's what caused it at Fukushima. What electrical systems we do have are triple backed up. We've learned from Fukushima, and we had 2 backups levels. We've gone to 2 more, so we have a total of 4 backup levels. Another reason is we are not the same kind of plant as Fukushima. Fukushima was what we call a boiling water reactor with a rather, I don't want to say primitive, but it was first generation containment structure. If you look right over here, that's a simulation of the walls of Palo Verde's containment structure. And our containments are domes. They are not a canister or a cylindrical shape with a bolted on top, so we don't have that capability. Anything that can happen inside the Palo Verde core can be contained by the dome that we have. That's been calculated. We know that. So that basically is why we can't have it. But the biggest reason is we're not in a location that's susceptible to those kind of things, and that was deliberately planned. It ain't for nothing that we built Palo Verde where we did. We did a lot of research to find out what would be a good, safe place to put a nuclear power plant, and that was one of the reasons. Not only is it relatively remote from people, it's in the lowest part of the state of Arizona for historical earthquake tremors, or whatever you call it, minor earthquakes. And there's a map somewhere, and I don't know, I've got it, I'll show it to you. But we are the lowest level of any earthquakes, in the state of Arizona. That's basically it. Anything else? We got everybody here? Looks like we got a good crowd.
Yeah, just a couple
All right.
more coming in a minute.
All right, we'll get them here. Let's go on in the auditorium, folks. You grab a seat. We're going to do a PowerPoint show. We got seats everywhere. There'll be plenty of seating for everybody.
Sorry, I didn't
Right
get a
there.
chance to ask you. My name is Brett Walters. I assume you don't mind a little filming.
Okay. No, I don't mind at all. Yeah. Come on in here, folks. Right in through these doors. And just grab a seat. I'm going to stand out here because I see these people coming in. They might not see where we're going. But just grab a seat anywhere. You can see we got monitors, screens everywhere. So wherever you sit, it's a good seat.
This looks pretty good.
You're gonna have that podium in between you and the screen.
No, because I've got it at the right angle.
You can split it, you get 3 neutrons per fission, you get the same amount of energy and all that stuff. So here we're making a byproduct that's useful. And the rest of the world uses that. They take their fuel and they put it somewhere and let it cool underwater for about 5 to 10 years. Depends on where it's been used in the reactor, how much heat you have left over. We call that decay heat, by the way. Okay. Then they will take this used fuel assembly and they will carefully shield it, because it's very radioactive now, and they will send it back to a plant. Plutonium's a different chemical element. We don't have to enrich anymore. Now we can use chemistry to pull it out. Pull out that plutonium, send it to the new fuel factory, voila. 4% plutonium, the rest leftover U-238, and I got brand new fuel for nothing. And that's called reprocessed fueled or mixed oxide fuel. Works fine. Palo Verde literally was designed to use 100% of it if it ever was available. But we do not do it in this country for political reasons only. A ban was imposed by President Carter on reprocessing commercial fuel. The ban was lifted by President Reagan, but he also vowed that the federal government would neither finance construction nor subsidize construction of these plants that would do this. And that's where we sit today. Nobody in its right mind is going to try to open up a plutonium factory in the United States commercially. Can you imagine that? Hey, the ABC company is going to bring plutonium through downtown Phoenix. Hi, come on in, folks. We're almost done, though. So, that's where we stand. We've got good fuel in here, but we can't separate it. So what happens? Well, we have leftover heat.
Quick question with that.
Yeah.
Because I know France reprocesses a lot of
They
this.
do indeed.
Do we repurchase it from them?
No, we don't right now. It's against the law to transfer ownership like that in the United States.
So we can ship it out, but we can't.
We
bring
can't
it
ship
back.
it out either, not yet.
I thought they did start shipping it.
No, we don't have the license to transfer ownership of it. Right now, the way the law stands, we, the utility, own the fuel, or the federal government owns the fuel, and that's it. So, what do we do? Well, first of all, here's the amount of heat that you get, and there's an example out front that shows this. 1 pellet is equal to 3 barrels of oil, 1 ton of coal, or 17,000 cubic feet of natural gas in energy equivalent. Okay. And here's how the fuel is taken out of the reactor. 1 fuel assembly at a time. It's all done underwater for 2 reasons. Heat-wise and also for radiation shielding. The water's a very good shield. We transfer the fuel from the reactor into the adjoining building called the fuel building, and that's where it stays. Now, originally, of course, we were going to reprocess. Then in 1987, Congress passed a law called the Nuclear Waste Policy Act. This law did 2 things. First of all, it imposed a tax. They all do, right? Yeah. So we had a tax. 1 mil per kilowatt hour that we generate has to go to the federal government. The second thing it did was it says the federal government will build a repository for used nuclear fuel and begin taking fuel by 1989. That's what the law says. Is this 1989? It must be earlier than that because they haven't taken a single stick yet. So, and that's where things like Yucca Mountain come in. These were designed to be repositories for a mixture of reason, not the least of which is politics. There is no repository for used nuclear fuel. And we were not designed to store 40 years, let alone continued operation, 40 years worth of fuel inside the pool of our fuel building. So we have gone to this. We have the space to do it. We have put 24 used fuel assemblies. Now, these are ones that have been in the water for such a length of time that the heat level has gone down to where they're just warm. If you could touch it. You couldn't because you'd be dead before you got near it, but if you could touch it, it would just be warm. We place these in a steel and concrete container. Each one contains 24 fuel assemblies, and we're just placing them out there on a concrete pad on the site. Right now, February 21st, just a couple of days ago, we had placed 111 of these casks containing 24 fuel assemblies. To give you an idea, that's how they're put together. There is an actual cast out front that's been cut away by the vendor so you can see what they look like and the size. And this is how they're transported very carefully. They're brought over from the fuel building on a flatbed rail car, and then this device carefully picks them up no more than 6 inches above the ground, and they're very gently moved over and placed on the concrete pad.
So does that thing submerge in the water when?
No. Oh, you mean to load it?
You gotta load it.
Yeah, it is, as a matter of fact.
Okay.
Remember, we were originally designed to reprocess fuel. So our fuel building was built with areas where these casks can be submerged, the fuel transferred underwater into the casks. Then there's a dam place where we can drain that little section, and it's filled with an inert gas, helium. Yeah. And vacuum dried and everything else. So there's no water in these casks. They're full of helium. Yeah. No, nitrogen. I take that back. Not helium, nitrogen. They're filled with nitrogen and sealed shut. Yeah. Yes.
Now, you mentioned when the fuel cell first arrives, it's
Yes.
only giving off alpha particles.
Yes.
When does it start giving off beta or gamma particles?
As soon as the first fission has occurred in one of the pellets. Beta is a particle of radiation. It's actually an electron, but we call it a particle of radiation. Is given off by the decay process of a fission fragment trying to get down to a stable state. Primary source of betas is fission fragments. Gamma rays are also given off by decay, but they're primarily directly caused by the fission process itself. Now, gamma rays, folks, are the same thing as X-rays. If you have a given strength of gamma ray, it would be the same as that same strength of an X-ray. Okay. We're almost done. I've kept you guys here a long time. That's what it looks like. That's our pad out there where we have our concrete casks. And we'll simply store those until the government decides to do something. We have enough space there to last the life of our plant.
And right now, go back to that slide for just a moment. Right now, how many years worth of storage is represented by 111 casks? How much operation of the
Yeah.
plant?
Well, let's see, 83 to 2011. I don't know. What's the math?
It's 28, I believe.
28?
So what we're looking at is 28 years of what a lot of people would call nuclear waste.
Exactly.
Although technically it's not waste, a lot of it is unburned fuel.
Yes.
The plutonium that we're not allowed
Yes.
to burn in the U.S.
Yes, absolutely. You got it 100%.
Is there also value in the fission fragments?
No, for two reasons. Number one, they're whatever isotope you might be looking for, you can get much easier from a purpose-built reactor. And the big supplier of radioactive isotopes, like for medicine and stuff like that, is actually Canada. They have a purpose-built reactor that can take, well, let's say iodine 131. If anybody's had a thyroid problem and they want to kill your thyroid, they'll give you iodine 131, which is the radioactive isotope of iodine. Canada has a reactor where you take ordinary iodine, bombard it with neutrons, and it turns it into that. So a purpose-built reactor is a much more economical way of doing it. So no, there's no use for it.
Okay. What about for technetium?
Technetium is a transuranic. It's there in, when I say transuranic, uranium, plutonium even absorbs another neutron, and under certain circumstances, it can keep kicking it up a notch to become still a higher element. And no, not a practical way of getting it out.
Okay.
Yes, sir.
How heavy are those caskets individually, and how would you transport those?
Well, you do it one at a time. I want to say, I don't know. Maybe it's outside on the placard right next to the canister, how much they weigh. I know to transfer it from our fuel building out to the pad, we have a special low boy flat car. It's a regular rail car, regular gauge rail tracks. And then we have the tracks that go into the fuel building. And that was built there when we designed the plant. And then there's a little special diesel-powered tug, basically is what it looks like. It looks like an airport tug that pulls that rail car out. We do it one at a time, but I don't know how much they are. I don't know why, but I want to say 21 tons, but I may be way off. Let's check out front and see if that placard says how much they weigh.
So if Yucca Mountain became active, they'd have to be transported by rail?
They would indeed. Rail or truck. It would be one canister at a time. They have designed, they being the Nuclear Regulatory Commission, has blessed designs for rail shipping canisters and truck shipping canisters. Now, what would happen is this. Let me go back. The steel inner canister would be removed. It wouldn't be placed in this thick concrete. What it would be placed in is one probably containing a good quantity of lead, because lead is an even better radiation shield, but it's not as thick. You have the weight, but you don't have the bulk. So there would be a specially designed shipping container that I don't have a picture of, if you're going to send it to Yucca Mountain or anywhere else. The inner steel container would remain. If Yucca Mountain comes into play, the fuel would never come out of that inner steel container. It would eventually even be stored there within that. Now, different overpacks, we call it, depending upon how it's going to go and where it's going to be placed. Yes, sir.
The contents of the 111 containers that you have out there, if we could refine it and reuse it, how long would it keep Palo Verde running?
I don't know. See, because first of all, that 4% is an average.
Yeah.
It's going to vary from fuel assembly to fuel assembly, depending upon its actual power operating history. That's an average. I don't know. Yes, sir.
The mines in northern Canada produce a product called yellow cake.
Yes, sir.
Two-part question, does Palo Verde eventually wind up using the product from Canada? And secondly, how many steps in the process without fail does it go through by the time it gets to Palo?
Yeah. Yellow cake is the name for uranium oxide ore.
Yes.
It is the way uranium is mined. That's what it looks like when it comes from the mill. Northern Canada is blessed with an extremely rich ore concentrate up there. In some parts of the mine up near Rabbit Lake in northern Saskatchewan, they're finding almost 80% pure uranium, which is unheard of. Think of a copper mine that has an ore of 80% pure copper, because that's what we're talking about. It's a mine. Because it is uranium, they have developed remote mining techniques that don't involve sending people underground. I'm not sure, but I think they actually blast it and dissolve it or something like that and bring it up as a liquid, whatever. Because use that leftover energy. You just can't do it.
I know you couldn't use it for generating electricity, but isn't there some other use for something that needs to be heated or?
No, and in fact, what we do is we maintain a vacuum in our condensers, okay, so that the steam remains steam below normal ambient temperatures. And we do that to get every little bit of energy out of it. Let me just hit this, and I don't want to bore you guys, but you brought it up. Why do we use water in energy transfer type things instead of, say, air? Why don't we just heat up air and use air for that?
Heat is much greater than
Huh?
water. Specific heat is much greater than water.
Exactly, and that's it. What he said is correct. When you take a pound of water at 212 degrees, okay, that's the boiling point at normal atmospheric pressure for water in our Fahrenheit system, right? Everybody agree? You just stick a thermometer in your point, okay. To go from 1 pound of water at 212 degrees to 1 pound of steam at 212 degrees, you have to add extra heat without changing the temperature just to make it change from water to steam. And it's that energy to transform the state is what we actually pull out of the steam. And that's why it becomes such a good vehicle for transferring energy. Okay. That's why we use water. No other fluid really has that capability. No other readily available fluid, okay? And certainly not air or anything else. So that's why we use water, and that's why we lower the temperature in our condenser, lower the pressure, so that it then converts back into water at a lower temperature. We get even more energy out of it. But we can't use anything other than what we do. Have I totally confused everybody? Nobody asleep yet, so okay. Well, yeah, all right. Okay. What's electricity? Anybody? Man, you're too good. Electricity is the movement of electrons, specifically in a conductor. We don't think of lightning as electricity, although it is, but from a commercial standpoint, it's certainly not anything we can use. So it is the movement of electrons in a conductor. So with this in mind, and don't you answer, how do you make electricity? What do you need to make electricity? Anybody? Over here. Yes.
Generators,
Okay, what's in a generator that makes electricity?
magnets, and conductors.
Electromagnetic fields.
Okay, exactly right. You need three things. You need an electrical conductor, a wire of some kind, to make the electrons move. You need a magnetic field, and you need motion between the two. That's a very simple generator. As that wire moves through those magnetic lines of flux, which is called a magnetic field, it causes the electrons to begin moving in that wire. That is a simple generator. Now, there is nothing in the laws of physics that says I can't keep the wire stationary and move the magnet. It only says I have to have motion between the two. So in large commercial plants, that's exactly what we do. This is the exhibit right out here, by the way, that you can see. We make this a huge rotating electromagnet. This is a picture of one of those in each one of our Palo Verde units. We have one per unit. We call it the rotor. It is a huge rotating electromagnet, and it sits inside that coil of wire we call the stator. That rotor is hooked up to the turbines. The turbines spin this rotor at 3,600 RPM, and as that magnet turns, it creates electricity in those coils of wire. Seems pretty simple. Why do we need a big nuclear plant on the other end of that rotor? Because the laws of physics say that the more electricity you try to create in that stator, the wires on the outside, it has a tendency to want to make that rotor turn back the opposite direction. In other words, what it actually wants to do is make that generator now a motor. And the more you make, the harder it is to turn that rotor. And that's why we have 4 steam turbines. Let me see if I can get a picture here of this. That's a picture of it. The generators, by the way, is at the far end here. That's not the generator at this end. We have 4 turbines, a high-pressure turbine and 3 low-pressure turbines, all hooked to the same shaft, driving a single generator in each unit. And this is what the picture of our turbine deck looks like, and each unit is exactly the same. So, how do we do all this at Palo Verde? How do we get that thing to turn? Well, this is what we do. We use something called a pressurized water reactor. It is not a new design. It was originally developed by the federal government for the first nuclear submarine, the USS Nautilus. When the Nautilus went to sea, she had a pressurized water reactor system. This system has proved so successful that every nuclear ship in the Navy right now uses exactly the same design, a pressurized water reactor. And here's how it works. In the red portion, everything you see in red right here is water. Pure, ordinary water. Very pure, but it's not heavy water. There's nothing exotic about it other than its purity. That water system is pressurized to 2,000 pounds per square inch. When you pressurize water, the higher the pressure, the hotter you have to get that water before it will boil. That's the principle behind the old pressure cookers. Okay? At 2,000 pounds per square inch, water does not boil until it's heated to about 610 degrees Fahrenheit. We don't heat it that high. We use the nuclear reactor right here in the center to produce heat and heat the water up to about 604 degrees. That super hot water then leaves the reactor and goes through, you see this little thin red line right here? That represents a tube, and in fact, it represents 17,000 tubes, each about the size of my thumb. These tubes are all in a bundle in parallel, going up and coming right back down then the water immediately comes out of there and goes back into the reactor to be heated up again. The water that touches my nuclear fuel never leaves the containment building and makes that trip, and that's it. Now, on the outside of those tubes, those thin 17,000 tubes, shown in green right here, is an entirely separate water system. It's also very pure, but that water system is not pressurized. So what do you think is going to happen to that water when it hits these tubes that are now heated to 604 degrees? It's going to boil. And that's where the steam is actually created, right in here. It then comes out of these devices we call steam generators. They're just heat exchangers. And the steam now leaves the containment dome and goes to turn the steam turbines. After it has done work, the leftover steam is brought to the bottom, and this is where our water from the water reclamation facility, our sewage effluent, comes in. It comes through here and removes the leftover heat from the steam. That turns it back into water, and we repeat the cycle. Yes, sir.
Is that the pink one?
I'm sorry?
Is that the pink color?
Yeah, it's the pink right here.
Oh, okay.
Just this little simple loop right here. Okay.
So that's the effluent.
Yeah.
Okay.
So now it's a question of volume. We have huge volumes of this cooling water going through, picking up maybe 5 to 6 degrees of increase in temperature. Now that water in the pink loop, this is the sewage effluent, not pressurized, picked up heat. It's now about 88 degrees. It goes to the top of the cooling towers. And our cooling towers are open on the sides and louvered. Okay. That water then falls down in the open, hitting these louvers, breaking up, and falling to the bottom where there's a pond at the base of each cooling tower. On the top of the towers are 17 huge fans about the size of a helicopter rotor that are all blowing up. So that is sucking air in through the louvered sides of the cooling tower, and it's no different than blowing on a cup of coffee to cool it. You're simply blowing air past this water, and that takes the leftover heat and moisture up into the atmosphere, and that's the cloud you see when you drive out towards Palo Verde.
So
Three.
The same concept is cooling for big commercial buildings.
I'm sorry?
Same concept. as
Absolutely.
cooling these commercial
Absolutely. Much bigger scale, but the same thing. It's the same concept as your air conditioner or heat pump works, except you don't use water cycles to transfer the heat. Any questions? Yes, sir.
I heard that there was a use of molten sodium in lieu of the water going around the reactor.
The sodium plant was the one developed for the USS Seawolf. Sodium is a metal that is a liquid in normal temperature and pressures. The advantage of using sodium is that with a metal you can transfer so much more heat than you can with water. The disadvantage is sodium and water do not mix. They react violently with each other. The other problem is that if it gets cool enough, sodium will solidify. And once you've solidified your reactor system, it's ruined. It's gone. It's shot. It's turned into a brick. So sodium never worked out. They used it in the Seawolf for several years, brought it back, took the whole thing out and put a Nautilus-type power plant in the Seawolf, and she became a very successful submarine using a pressurized water reactor.
So
Any other questions?
there's no sodium at Palo Verde.
No, sir. Well, I take that back. I don't know. In a lab somewhere, there might be a small sample of sodium or something like that.
Not in the reactor system.
No, not in the reactor. Absolutely not. No sodium in the reactor. Unless it happens to be a fission product inside the fuel. Yes?
What is the difference between operational-wise a can-do reactor versus this?
Let me go to the next slide. This is the module and how it works. You can see it out there, but I wanted to go to this. That's a can-do down there. A can-do uses nuclear physics to create the fission process slightly different. They use natural uranium. The uranium does not have to be processed other than being purified. So it's called natural uranium. However, to get the fission process to work, they have to use what's called heavy water. And the CANDU units, Pickering for one, has to make heavy water out of regular water. You don't make it. I take that back. You cannot make heavy water. First of all, heavy water, let me explain what that is. Water is H2O. We've all heard that. That's 2 atoms of hydrogen for 1 atom of oxygen. That's water. Hydrogen as an element can exist in 3 different isotopes. An isotope simply means 2 atoms of exactly the same thing with different number of neutrons in the center. Okay? So, hydrogen can exist 3 ways. Normal hydrogen has no neutrons in the center, just a single proton in the center of it. It can have 1 neutron, and then it becomes something we call deuterium, or it can have 2 neutrons, which does not really exist in nature, but can be created, and that's called tritium. Deuterium exists in everyday water, but in very, very minute quantities. So what they have to do in the CANDU plants is they have a special, almost like a fractional distillation thing, where they take water from the St.
Final question.
Yeah.
With respect to that. You may be biased in the answer to this, but with respect to the CANDU versus Palo Verde, which is the more efficient in terms of cost of kilowatt produced or megawatt?
Palo Verde.
Is it?
The reason for that is because of economy of scale.
Okay.
CANDU, by its very principle and by the mechanics associated with, not the physics of it, but the mechanics associated with having to do a CANDU plant, you're pretty well limited to about 700 to 900 megawatts capacity, whereas Palo Verde is 1,400 megawatts. So we've got an economy of scale in that. Yeah. CANDU plants don't exist really outside of Canada. They've sold some to the Indians. They have some features that are very desirable. They can refuel on the fly, but they've had problems with the fuel cans that they put it in have deteriorated and so forth. So it's really kind of a wash, is what it boils down to, but not as economical. Any other questions on that? The one on the left, top left, is Chernobyl. Chernobyl is a type of nuclear plant that has never been built anywhere outside of the old Soviet Union. And in fact, those that are there are being dismantled. Chernobyl plants had the distinction of having to have something added to their reactor core to make them work, and that's those blue slabs you see in there, and that is graphite. Graphite is used to slow neutrons down in the particular design of a Chernobyl plant. Chernobyl also had certain other control variances that were very undesirable. I don't want to get into that other than to say it had to do with how the plant reacted to changes in temperature of the cooling water. Okay, it had a tendency to act violently in the wrong direction for changes in cooling water temperature. Okay, but it had to have graphite in the core, and graphite is a form of carbon, and graphite will burn. Anybody here old enough to remember the old carbon arc searchlights that they had? And movie projectors used to have 2 rods of carbon that would produce the light and all that stuff. So anyway, it will burn. In April of, what was it, 83 now or something, that Chernobyl had the accident? It's been a while, 86 maybe. They overheated their reactor by doing an unauthorized drill test. They overheated their reactor at a certain spot, and it caused a steam poof, if you will, in that one location within the reactor. And I don't know if you can notice, but there is not a bolted on top to their reactor vessel. It's simply a concrete slab. And this slab lifted just ever so slightly, and it let air get into their reactor vessel. And that air reacted with the graphite and began a fire inside the reactor itself. For 9 days, their reactor burned. As it's burning, it's melting fuel. This fuel is being caught up in the smoke and coming billowing out of the containment, which isn't a containment at all, but simply a warehouse type shed. And that spreads for 30 miles out in the countryside. Okay? Differences? We don't have plants like that. We have strong containments, And we don't have anything in our reactor to act as a vehicle to carry products from the fission process out into the countryside. Yes, sir.
Well, you're talking about other type of nuclear plants. These are all uranium based, right?
Yeah.
But you haven't got into thorium. Is
Well, there is
anybody-
no working thorium plant yet.
I know they're working on it.
Yeah. Thorium is another, it's a fissionable material, but not fissile, which means that you can make it so that it will split, but it doesn't split on its own. Okay. It's an element that's in great abundance in certain parts of the world, particularly in the Indian subcontinent. And it has the benefits that if you surround a particular design of uranium reactor with thorium, this thorium will then be exposed to neutrons that are being given off by the nuclear uranium part of the plant. And thorium can then be converted to an artificial, not existing in nature, form of uranium called U-233. This, folks, is what they call a breeder reactor. You actually are taking a relatively common material called thorium, surrounding a reactor with it, and turning that into useful nuclear fuel. You are breeding fuel as you go. Okay. They're working on setting that up. They don't have one in operation fully commercially yet. There's one being built. There's a couple being built that they're trying to use it for. The advantage, of course, is that you're breeding more than you're using, and you're using a material that's in better abundance in certain parts of the world. Any questions? Did I answer that on the breeder? Okay. That's all I'm going to say about breeders, because there really aren't any breeders in our country that are in operation. But we will talk about something left over as a byproduct in just a bit. Am I boring anybody? You want to get out of here and say, let's go for breakfast? Or... All right, here's some views of our control room. I just wanted to show you what it is now. We have 5 licensed operators in each control room, 24 hours a day. 2 of the operators are actually supervisors, and they have what is called a senior reactor operator license issued by the Nuclear Regulatory Commission. And then 3 licensed operators. And we normally kind of divide the control room into thirds, and that's sort of their area of responsibility. The units are identical. Therefore, we only need 1 license that covers all 3 units. Our operators can then go to any unit because they're exactly the same. So much so that we even put 2 in there to indicate that that's unit 2. Okay? The operators are pulled normally from current employees who usually have started out and are working as what we call auxiliary operators. And these are simply people that go in the plant and they're in radio contact with the control room, and they might say, go open this valve, check this oil, that type of thing. They're roving watches. Then when we are ready to need more reactor operators, we will start a class. And the training for a reactor operator takes about a year. It's a combination of classroom work, and we have 2 exact copies of our control rooms. However, they're simulators. They're run by computers, and we have those in a separate training facility, and we can train the operators on there to different accident scenarios. Okay. It takes about a year for an operator to get to the point where he's ready to take his examination. The examination itself takes a week to complete. It is combination written and in the simulator, throwing drills at him to see how he does. And our operators, it always comes up, our operators do make 6 figures. Okay. Their pay is structured in different ways, but usually they make at least $100,000 a year plus. Okay. They do not require a college degree to be a reactor operator. However, the training is academic. It is textbook type courses, very accelerated, but it recognized as being just that, and there are about 6 or 7 universities in this country that will recognize all of that technical training to meet all the requirements for a Bachelor of Science in Nuclear Technology. So most of our operators then just go back and somehow pick up the English and the literature, whatever, the other courses they need, and they in turn do have degrees that they got courtesy of the training they get here to be operators. Not required, but most of them have it. Okay.
That actually sounds like the fastest way to get a nuclear engineering degree
Not engineering,
possible.
I said nuclear technology.
Okay, nuclear
There's
technology.
not enough math to be the engineering degree, yeah. Yeah, it's a good way to do it, and you gotta consider a lot of our guys came from Navy nukes. In which case, the class here is kind of just a redundant, because we had all that in nuclear power school, which is much tougher. Navy nuke school is much tougher than what we do here. Any questions? Am I going too slow? Too fast? Just right? Okay. We're getting to that. We're gonna get into the physics of it. Where do we get the heat? Where do we get the heat? Remember, all we're trying to do is heat up water to make steam. You can do the same thing by burning coal or natural gas, but we don't. We use nuclear physics and nuclear technology to perform heat without producing any harmful environmental effects. To do that, we have to understand, first of all, this is an atom. The center part of an atom is called the nucleus. It is comprised of protons and neutrons. The outer part are electrons. Forget electrons. We're not going to talk about those. We're talking about the center part, the nucleus, hence the word nuclear power. Okay. All elements. There's 92 naturally occurring elements. Yes, there's more than that, but they're not naturally occurring. 92 naturally occurring elements from 1 to 92 designates the number of protons in their center. Hydrogen has 1, uranium has 92. But you could have two elements of exactly the same atomic number with different number of neutrons. When we do that, we say we have two isotopes. And in the case of uranium, it occurs in nature two ways. It's all going to have 92 protons because that's exactly what makes it uranium. But it can have 146 neutrons or 143 neutrons. We add the two numbers together and conveniently call it U-238 or U-235. That's it, folks. That's the way it occurs in nature. No matter where uranium is mined, and it is dug out of the ground, like iron or copper, no matter where uranium is found, you will find the same distribution between those two isotopes. Almost all of it. 99.3% of it is U-238. Less than 1% of it is U-235. And of course, we can't use U-238 to make fuel. It doesn't work.
That'd be too easy.
It would be, wouldn't it? It'd be way too easy. We have to have U-235 to make nuclear reactor fuel or to make a uranium-based nuclear bomb. Okay? So, in the case of both of those, how do we get enough U-235, or more accurately, how do we separate the U-235 from the U-238 when they're both exactly the same chemical element? Can't use chemistry. They're going to react exactly the same way. So, it has to undergo a process called enrichment, and this is a physical process. Currently, there are three ways that enrichment is done. It's the old gaseous diffusion, which was done originally to make the first atomic bombs and all that. There's the centrifuge, and then a newer technology called laser separation. In all cases, it relies on the fact that U-238 has 3 more neutrons than U-235. That makes it infinitesimally slightly heavier. And in a centrifuge process, that means that the U-238 is probably going to go out further towards the outside of a centrifuge than the 3 neutron lighter U-235 is going to go out. So what we'll do is we'll put a drain on these centrifuges, maybe about halfway out, and take what's off there. Now, yeah, we're going to get some of the U-238, but some of it has gone to the outside. So let's take what we've drained and run it again. And we're going to run it again. And we're going to do this for months and months. Each time, just a little bit of the U-238 has been sort of pushed aside. We are not changing the atoms one iota. We are simply segregating away some of the U-238. That means that our total quantity is going to be less, but now we have changed the ratio between U-235 and U-238. And that's called enrichment. If we wanted to make a bomb, I have to get rid of almost all of the U-238 because not only does it not work, it doesn't split and do what we want it to do, it robs the process of neutrons that we need to cause the fission. So it acts as what we call a poison in the process. So to make a nuclear bomb, I have to have almost pure U-235, 92% pure or better. We can't afford that, nor are we allowed to do that for fuel at Palo Verde. Our fuel is only allowed to be enriched to 4%. 4% U-235 from 0.7%. That's it. All the rest of it is U-238. So that's number one, why we can't go off like a bomb. We haven't got the right enrichment. Okay? That's all it's done to the uranium. It's enriched to 4%, and then it's sent to a factory that takes this stuff and takes this uranium and makes it into little pellets. Okay? It's compressed into small pellets about the size of a pencil eraser. And then these pellets are stacked inside long, thin metal tubes. And you saw a bundle of them outside here. These tubes hold 200 pellets. They're then pressurized, because remember, this is going to be inside the red system that's pressurized to 2,000 pounds per square inch. So we got to pressurize the tubes so they don't crunch up. And the tubes are sealed. They're bundled together into what we call a fuel assembly, and that's what we buy. That's what it looks like when it goes in. That's what it looks like when it comes out, because everything is happening inside the fuel pellets. And there's an example of it. Yes?
What do they pressurize it with?
I want to say nitrogen, but it might be helium. It's nitrogen. Yeah. Not air. Yeah. It's nitrogen. It has to be something because of the nuclear properties of it. Yeah. It might be helium. It's probably inert or something. I don't know. Very seldom do I make fuels when using it. It's a good question. I'm going to have to look that up. I think it's nitrogen, but I'm not positive. So, yeah. Okay, any other question? That's the fuel. Now, the whole question now is what happens inside the fuel that makes the heat? And we'll go through that real quick. Each reactor, 241 fuel assemblies. We start up the plant, run it for 18 months. Each unit, they're exactly the same. Run them for 18 months, shut it down, and then we'll start taking it out right in the center because it's like a charcoal barbecue. Most of the activity is going to be right at the center, like a charcoal grill, right? That's where the bricks are the hot. So those are the ones we remove, take the outside ones, move them in, and take fresh, put it on the outside. And we do that every 18 months, just like that. So one fuel assembly will last us, 3 of those 18-month cycles are about 4.5 years. I just wanted to throw this in. It doesn't belong anywhere. But to give you an idea, how do we get such tremendous power? Well, you've got to realize how small uranium atoms are. Any atom, for that matter. So I was able to calculate, since very conveniently 1 pellet is 1 gram, so using Avogadro's law, I was able to calculate how many atoms of uranium are in 1 fuel pellet. How many atoms? And that's the number. I mean, it's astronomical. It boggles your mind. It's, it's sextillion atoms. But that's where the energy is. It's such a concentrated form of energy when you start splitting these little teeny atoms. Yeah. Okay, so, and this is the power of the pellet. It's out there. You can go over this stuff. But here's the whole key. How do we get heat from this process? Well, here's what happens. What you see there is an individual U-235 atom. That's right in the center of the screen here, or slightly to the left. The U-235 atom is sitting there fat, dumb, and happy, and a free neutron traveling at just the right speed. I'll tell you where these come from in a minute. And this is a random process now. It's not anything we can guide. But if this neutron happens to hit this U-235 atom, like this, it will cause that U-235 atom to split, and that is nuclear fission. In addition to splitting, I didn't show it, I don't think. Did it show the 3 neutrons coming loose?
Yeah.
Okay. It also releases, on the average, 3 free neutrons, and that's the whole key to how we can get this thing to run. Once we cause fission, we need something in the reactor, because we can't do this manually, something in the reactor to slow these neutrons that are released down. And then those neutrons can strike more U-235 atoms and keep this process going. And what you use to slow a neutron down is something called a moderator. A moderator is like a white cue ball striking a bumper on the side of the pool table. That cue ball is traveling fast. It gives up some of its energy to the bumper, and the cue ball starts going slower. And that's exactly what happens. The neutrons have to strike something in there inside the fuel pellet to get it to, well, not inside the fuel pellet, but inside the fuel, inside the reactor, because they may go halfway across the reactor. But if they strike something and can give up some of their energy, that neutron begins to go slower. And we call that process thermalization. And you know what they really strike to give up their energy? The hydrogen atom in the water. Our water acts as the moderator. It takes energy from those neutrons, slows them down. Now they're going slow enough to cause more fissions. Once we start this process, it's going to keep going until we do something to stop it or run out of U-235 atoms. The graphite in Chernobyl took the place of the water. They used graphite as a moderator. Now, how do we stop this thing? How would you stop it? What would you do to stop this chain reaction that's going now? You've got fissions, neutrons slow down, more fissions, slow down, more fissions, slow down, more fissions. How would you stop this process?
Change the moderator.
Do what?
Change the moderator.
You could do that. In fact, you can. We could change the heat demand coming off the water, and that will cause the water coming back into the reactor to be a little bit warmer because we're taking less heat away from it. That makes the atoms of hydrogen in the water a little further apart, a little harder for the neutrons to find it. That does work. Works extremely well on nuclear submarines, but that's for a different reason, but it does work fine. Yes, we could change the moderator. What else could we do? From an engineering point of view. He said move the rods further apart. That's not really practical to do that.
Put a shield between them.
Do what?
Put a shield.
Shield against what?
Well, between your columns of uranium columns.
Yeah, you could do that. Again, mechanical solution, a little hard. How about if we just absorb the neutrons? Soak them up. Would that work?
Yeah.
Yeah, and that's what we do. Somebody mentioned control rods. That's what a control rod does. It soaks up neutrons and does nothing with them. Okay, this is out there how it shows where it's doing. We soak up neutrons and do nothing with them, and the reactor will shut down. If we want to shut it down in a hurry, we release the latches that are holding control rods out of the fuel assemblies. They drop into the reactor, and that process shuts down in less than a second.
Question on that, how come that didn't work in Fukushima?
It did.
Because they had the control rods, I mean, they showed demonstrations where they come up from the
They
bottom.
do come up at the bottom in a boiling water reactor,
Right.
but the reactor shut down. They just couldn't keep it cool. And that's the whole crux here. You've got to be able to keep it cool after it shut down. Because what's really happening, when you split that uranium atom, the energy, 99% of the energy, is kinetic energy in those new halves of the uranium atom, which we call fission fragments. They're actually new atoms of new substances. Krypton, xenon, these are new elements, or elements that are lighter than uranium. And these guys have so much kinetic energy, and kinetic energy is energy of motion, that these fission fragments are doing this inside the fuel pellet. Bam, bam, boom, bow, bow, like that. And I'll give you a good example of how that causes heat. How many of you have ever taken a paper clip or any piece of metal, doodle it around, you just start bending it, right? Okay. Pretty soon, what happens? Why does that paper clip get hot? It's not transferring heat from your fingers because it's getting hotter than your fingers. So where's that heat coming from? Of what?
The metal atoms.
Exactly. You're physically making those atoms move by bending them. We're doing it by giving them energy from their birth. And they are moving around inside that fuel pellet, and that's where the heat is coming from. And this is also the Achilles heel, because yes, every time they hit something, they're going to give up a little bit of energy. The pool table again, okay? The balls hit something, every time they hit something, they go slower, right? But they still move, all right? Unless you're a really good shot, okay? All right. So, until we've given up all the energy that these fragments have, they're going to continue to generate some amount of heat inside my fuel. We call that decay heat, and we always have to keep our fuel cool at least for the first 4 or 5 years after we've stopped the fission process. It's like a burner on an electric stove. You got to let it cool down. In our case, we keep it underwater to cool it down. Okay? Yes, sir.
Is that what meltdown is? If you can't keep it
Exactly.
cool?
Exactly. A meltdown is where you've lost the cooling capability, particularly right after shutdown. The heat inside the pellet is sufficient to actually melt the tube. Yes. That's a meltdown. Okay.
After 18 months, what's the percentage of U-235 still left?
Do you see the slide? Did everybody see the slide? Okay, good. New fuel assembly goes in because this is something else that goes on. I put new fuel in, and remember I said the maximum enrichment we can do by law is 4%. So instead of being natural uranium, which would be 99.3% U-238 and 0.7% U-235, our fuel pellets going in are 93% U-238 and 4%. I'm sorry, 97 U, whatever. Yeah. Okay, 4% U-235. All right. Now, it's been in there for 4.5 years. Changed location. This is the fuel assembly. Changed locations. Now we're ready to take it out for good and put it into our storage because we got no place to send it. That's another story. Okay. What's in our fuel pellets when we take it out? Well, we can do an analysis. We find out that after 4.5 years, the used fuel, 94% is still U-238. That makes sense because I said it's not, it doesn't fission or anything like that. So it makes sense that a lot of it's going to be U-238. Fission products. That's what happens when a uranium-235 splits. These are called fission products. We also call them decay products. They're also called daughter products. They're all the same thing, okay? These are the remnants of a split U-235 atom. When you add that up, 94 and 4, that doesn't come up to 100%, does it? So what else is in there? Plutonium. U-238 will not fission, but U-238 can absorb a neutron. And when it does, it's like the MRL cooking show, bam, kicks it up a notch. And it goes up one notch on the periodic table and becomes an element that didn't exist in nature until the Manhattan Project. And that element is plutonium. And guess what works exactly like U-235? Plutonium. Now, of course, the Manhattan Project was looking for a way to get something that they could use in a bomb, and the enrichment process of U-235 was taking them forever. They had these facilities at Oak Ridge. They were running them night and day, and they were measuring it in micrograms per month is what they were getting by enriching in those days. But they also built reactors up at Hanford, Washington, very primitive ones, but they used uranium in there and were able to take the fuel apart when they were done and pull out the plutonium and use that to make a bomb. And that's what they did to make the first bomb they tested in New Mexico. That was a plutonium bomb. They actually blast it and dissolve it or something like that and bring it up as a liquid, whatever. Because of yes, uranium doesn't have a lot of radiation, but if you're down in a mine surrounded by it, then it's a different story. So anyway, it comes from the upper mine. It's owned by Chemco, which is Canadian-American something. I don't know. I bet the people. Anyway, yes, we do use some of it. They're a very big supplier of ours. We also get some from Chemco mines in Australia. And as I was telling some of the people out front, we also buy some as Russian diluted warhead uranium. Okay. It's all part of a mix. Now, here's the steps, and they're individually contracted for by our fuel department. First of all, we have to buy the ore. We have to buy the yellow cake, okay? And that's spot market. We either have long-term contracts or spot market. It's like if you had a pipe making company and you were making copper pipe, you would have to buy the copper ore, and you could either do it on long-term contracts or spot market, depending if you were caught short or whatever. Same thing. The uranium ore is concentrated, purified as a mineral, and then it is sent to a conversion facility. And what the conversion facility does is it mixes the uranium with fluorine gas through a chemical process to produce a chemical compound called uranium hexafluoride. This is the only known chemical compound of uranium that exists in a gaseous state under relatively normal pressure. So it's strictly a chemical and physical process. Now stored in what looks like farm-type propane tanks, the big round cylinders with the thing on the top and all that stuff. Big tanks like that. This uranium hexafluoride is now shipped in tanks like that, and that's called the conversion process. That then goes to the enrichment facility, where in a gaseous form, the uranium is now enriched. It is still then from that point in a gaseous state. It is then sent to the fuel fabrication facility that takes the now enriched uranium hexafluoride, gets rid of the fluorine and makes it uranium oxide again and compresses it into pellets. The pellets are then put into the tubes, and all that's usually done at one facility. So the fuel fabricator gets it as uranium hexafluoride gas enriched to 4%. Does that answer your question? Good. Now, each step is individually contracted. I mean, we have a whole department that wheels and deals, we trying to save money on this. Under regulation, but still trying to save money. Yes, sir.
There was a mention earlier about thorium reactors, and also from the audience question, and also related to that, I think a few of us might be familiar with some of the new reactor designs that are being looked at. I was thinking that it might be possible to use the nuclear, not waste fuel. What do you call it again? Used fuel to be able to run those reactors. In other words, the two reactor types would be complementary to each other.
So there's a question in there, right?
Yeah, I was wondering what you thought of that as being possible.
Well, you're not going to be able to use used fuel to start something up. Remember, fission is caused by neutrons bombarding the U-235 atom. These neutrons are a product of a fission somewhere. Sometimes they're also created by the spontaneous disintegration of a fission product, some hours, months, weeks after the fission event. I've got an atom here that was originally part of the uranium nucleus, and it spins out a neutron to try and decay. Remember, everything radioactive, everything is trying to get down to a zero energy state, trying to get down to a stable level. And it does that by shooting out either particles or a ray to get its energy down. Nature wants everything down in equilibrium. Okay. To make a reactor work or to make a bomb work, you've got to have at least one of those three neutrons has got to cause fission. If it doesn't, you're on a downward rate of fissions, and eventually it's going to stop. Well, in a bomb, you want all of these fissions to occur almost instantaneously together. Because as soon as you have one split like that, it's going to push the other atoms away. And they might be too far apart now for the neutrons to do their work. So, in the case of used fuel, we've got that situation where now we've depleted it so much, we really don't have enough source of neutrons to get something fired up in a new reactor. That's why we took it out in the first place.
Okay, but what I was really talking about was maybe a chemical separation, take out the plutonium, and use that as part of the fuel. Maybe not necessarily the startup load, but the fuel for a next generation reactor.
That's what you call a breeder. That's exactly what a breeder is. You have a basic reactor, and you can run it on uranium or plutonium, either one. But the neutrons that escape from the core, in other words, the reactor vessel, you have a lot of neutrons that are escaping from that. Those can then strike thorium as a blanket around the outside, and that is indeed what we call a breeder reactor. Now, that's one design. But in all cases, thorium is looked at because it's so plentiful, particularly in countries like India that have an abundance of thorium, but they don't have an abundance of uranium. But we're not in the business of making reactors. We're in the business of producing electricity. So.
No, that's fair. I was just trying to ask if you could basically use up the fuel in an alternative reactor. That's basically the question.
It could be. I guess anything you could do. I don't think it would be economically feasible, but yeah. Reprocessing is feasible to extract that plutonium. And the beauty of that, what he's talking about, you take used fuel and it's got some leftover U-235, in fact, actually about 1%, and then it's got leftover plutonium. You extract that out, and that is economically. Plus, now your nuclear waste has been reduced in volume. So you have less that you have to worry about for ultimate disposal.
And even better than that, it's the longest lived component of the waste. The thing that people really hate and fear is the 100,000-year-old waste problem.
And that's plutonium.
And that's plutonium. You take that out and you burn it, you use it. Now you've basically mitigated your waste problem.
You have. The rest of it becomes no more radioactive than uranium after about 600 years. So that would be a solution, yes. Use the plutonium. Now you've reduced your volume and you've reduced the lifetime that it is radioactive. So that's it. Anything else? Any other questions? Yes?
Are you allowed to talk about plant security?
Talk about what?
Security.
Yeah, I don't know what I could talk about, what you would want to know. Do you have specific questions?
Well, you know, people just decide they're going to
You can't get in the plant. You can't even get off the road anymore. This is a result of 9/11 primarily, and also some designs we made for efficiency's sake at the plant. Let me give you an example of what I mean by that. We built two maintenance facilities that we use to support any work we do during a refueling. Now, we call our one period every year and a half that we shut down a plant, we call that an outage. It's a planned outage, and to be economically efficient for our company, the whole concept is to make that outage as short as possible. Ergo, more time that you're at full power making electricity, right? Okay. So we do everything we can to shrink that window that the plant is down doing maintenance, doing refueling, and all that stuff. Well, the refueling part of that window is not the controlling factor. That's relatively quick. Like I said, we normally get it down to about 30 days. And the refueling part is not the major controlling factor. It's maintenance on all the other components. Things we cannot do while we're online. Case in point, inspect a turbine. Okay. Take a turbine apart. Look at the blades. Make sure we don't have erosion. Take major pumps apart. See if we have cracking of the impellers or any of that stuff. So anyway, to that end, we built 2 huge maintenance buildings to support outages. And now we've changed our perimeter boundary of our next to highest security level to encompass those buildings, and that's precluded us having anything on site for visitors. Where we used to have it, voila, it's now inside what we call the protected area. And folks, you don't go into the protected area unless you've had a complete police background check, a psychological profile check, including an interview by a psychiatrist, drug and alcohol screening, special training, all of that stuff. I don't have it yet. I used to have it. I don't even have it now. Because if you don't use it every 30 days, you start from scratch. So, and that access is controlled by biometrics of your handprint versus the card that you carry. So anyway, that's why we don't go on site anymore. Now, security itself. We have a armed security force. They are APS employees. By law, they are the only people in the state of Arizona, including the police forces. Our security force is the only ones that by law have the right to shoot to kill to protect property. So if you try to mess with the plant and try to get somewhere where you're going to endanger the safe operation of the plant, they will shoot and kill you. No questions asked. So don't try it. Don't test it. You wouldn't get close enough to test it, but don't anyway. Anything else? And we do have drills. Yes, we have drills periodically. They bring in Army Rangers and SEAL teams and guys like that are part of professional interveners. And of course, they don't use live ammunition. We don't want to lose SEALs. But they do use laser guns, I guess, or rifles with lasers on them. And nobody's ever penetrated to the point where they can shut down both trains of our safety systems. And I didn't mention that. All of the systems that are needed to keep the plant in a safe, cool, shutdown condition are duplicated. We have 2 of everything, 2 sets of pumps, 2 sets of electrical supplies, 2 sets of conduits, piping, 2 separate rooms separated from each other that contain these 2 trains. Yes?
Can that place blow up?
Can what?
Could it blow up?
No.
It just doesn't melt down.
It can't blow up because it can't. You talk about a nuclear explosion?
Yeah, or something like that.
No, you missed that part, and no, it cannot. It does not have the right uranium, nor is it in the right concentration together to do that. It cannot blow up. It cannot even have really a steam explosion, although you could have a poof like that inside the containment dome, but it's built to withstand that. So no, it cannot blow up. It doesn't have the right uranium for it in the right quantities. Right? Everybody agree? We're all coming out with at least that knowledge, right?
Now, I have a question.
Yes.
How do you handle if there was a containment issue? You know, you got the pressurized system with all the looping rods
Yes.
with the water. What happens if one of those rods ruptures and you mix the coolant with the radioactive
It's what we call fuel failure.
fuel cell?
And it has happened. First of all, we're sampling every 4 hours. We sample the primary coolant to see if such a thing has occurred. It would never usually be a catastrophic failure like you're thinking of, but perhaps a pinhole leak or something like that caused by rubbing or whatever. In which case, we would immediately shut down if it reached the threshold level of radioactivity, and we would depressurize. Now, meantime, the coolant is going through filters. Okay, I showed a very basic diagram.
Right.
The coolant is constantly going through special filters, and the contamination or that radioactive component is now trapped in the filter medium. Okay. That filter medium can be removed, and that is sent to what we call a low-level waste burial facility. There's about 10 of them, I think, in the United States, licensed by the government, and that's where that filter medium would go. We would shut down. We would try to do what we call a reconstitute of that fuel assembly. Pull out the bad pin, put a good one in, and that would just be stored in the fuel pool. But the whole key now is to not let that happen. So we go to great lengths to make sure that the water is absolutely pure. There's no pieces of grit or anything that could scrape the fuel pins. Okay. We do a close examination. We make sure that the vendor who makes the fuel has not created any weak spots in the tube wall. Okay. So it's a whole process to eliminate that.
Right, right,
Yeah.
but things happen.
Well, yeah, but less and less.
Agreed.
Yeah. Things could happen. We're ready for them if they do. They have happened in the past, but they happen less and less because of multiple safety systems, multiple barriers, training, procedures to do everything. There's a term we say, think like a nuke, and it's not like anything you guys have ever had. You think in terms of procedures and steps that you stop and do. If you thought like a nuke at home, it would take you a week and a half to cook dinner. Yes?
So what happens at the end of the life of a plant that makes the plant no longer usable?
The primary concern is kind of twofold. Number one, the technology has just gotten too old that you can't find replacement parts, and we're getting there on that. You can't find components to replace those that have worn out. Keep in mind, we got to have the same stuff because that was the approved design, okay? So you can't find vendors. The other thing is something called neutron embrittlement. The steel pot that all the fuel is in, we call it the pressure vessel, okay? And it's really just a carbon steel pot that's fully lined with stainless steel to prevent corrosion. Over the years, neutrons from fission have been striking this carbon steel pot because not all of them cause fission. Remember, only one of 3 is needed to cause fission. The rest of them just can be going in. Over a long period of time, these neutrons are striking the steel in the pressure vessel, and it can make this steel become brittle. It's called neutron embrittlement. It's not unlike taking steel, heating it up, and quenching it quickly. It makes it brittle, it makes it very hard, but it's very brittle. Brittle is not what we want because then under heat up or cool downs, we could get stress cracks. You don't want that. So to measure this, to measure our effect of neutron embrittlement over the life of the plant, when we built Palo Verde and put the reactors in, we put samples of the carbon steel inside the reactor vessel. Anybody familiar with the Sharpie V-notch test for metallurgy? That's what these are. They're little metal slugs made of exactly the same material as the pressure vessel. Every 10 years, we pull one of those samples out and we test it. And it gives us a data point. And we know just how brittle the reactor vessel is coming by testing these samples that we put in there because they're exposed to the same radiation. They're inside the vessel. We thought we would have a problem in 60 years, but we're not. It's getting much better. But the ultimate is going to be just simply technology overtaking what we can provide to replace it. And we're not close to that point, but you would be surprised going into a control room and seeing all the 1970s, 1980 instrumentation, switches, and all that stuff that are in there. It's hard finding vendors now to replace the like part. Yes, sir.
My last question.
Yeah.
I promise.
You promise?
We all know a particular country that's got centrifuges spinning by the thousands or
Uh-huh.
millions, I don't know how many. What is the simplest and most efficient way to stop it? By another.
To stop them? Well, I don't know. That's outside my spirit. Maybe you got anybody here a computer nerd? Somebody would say a worm, a computer worm,
Apart from an I-8 bomb.
a bomb. You're going to have to blow it up. Unfortunately, they're doing all this inside a mountain, so I don't know. Well, that's a military question. I'm not a military man. I don't know how you'd stop it. Diplomacy, threats, military action. I don't know. It's a good question. Yeah. Yes, sir.
What's the technology used in Europe for their plants?
Technology for their plants.
The same as Palo Verde, is it?
Yeah. Oh, yeah. Pressurized water reactors are by far the most common type of reactor worldwide. They're about 75% in the United States are pressurized water. The only other kind would be a boiling water. I didn't talk about that because that's not what we have. A boiling water reactor simply eliminates the pressurized water part of heating a second loop of water. They actually boil the water directly in the reactor, and then the steam goes directly to the turbine. It's a simpler system, but now you've contaminated your turbine, so it makes your maintenance more complicated. It's a wash. Simpler design, more complicated maintenance, more expensive maintenance. And it's a good system. Fukushima was a boiling water reactor. Europe has pretty much the same as we have here. In fact, France years ago took a Westinghouse design and said, we're going to standardize this. They bought it from Westinghouse and then said, sayonara, or au revoir, I guess they would say. Took that design, refined it, and standardized it, and made all their plants exactly the same. Now, they can do that because France has state-run utilities. So they can standardize it. We have literally 102 prototypes in this country because everybody went out and decided to get something different. France made them all standardized, but they're all pressurized water reactors. That's all I have in here. You're welcome to spend as long as you wish outside. I would suggest starting through here and perhaps wandering around. There's a good display that has a moving graphic that shows where buildings are located on the site, that you can see that part. Different jobs, things like that. Take your time. I'll rove around. If you got any questions, I'll be glad to answer them. So, thank you.
If we want to come back with one.
No, you're not coming back in here. I'm not bringing you back in here. Is that what you're?